We have a student from the class of 2017 rejoin the program. It's my pleasure to introduce to you Zhu. He was in the 2017 batch. A few facts about him that I still keep fresh in my mind is he's an Aggie. What class are you, Zhu?
Oh man, not easy.
We're not talking about that, right? He's an Aggie. He has an advanced degree. He serves as a database. Are you a DBA also?
Not anymore.
All right. Other fun facts about him, he was a photographer when we were interviewing him. He was a photographer for the Houston Rockets. He was good friends with Dwight Howard. And then also, Junru was the first admitted student out of the 2017 group. So took a leave of absence. He had some stuff that he needed to take care of. Now he's back. Please note, make him feel at home. Teammates, he's told me that somebody has reached out to him. He's a great guy. If you have time, just come in and introduce yourself to him, please. Junru, welcome back.
Thanks. Appreciate it.
So let's talk about stat625. First, thank you for the comments from Dr. Jones in particular. You've got an incredible semester. You don't know 1/10 of the story. What that guy did was incredible. But beautiful comments, beautiful comments. Remember I got on my soapbox at the start of the semester? And there's going to be an epilogue to that, but we'll get to that. Very helpful comments for Dr. Jones. In particular, one of the comments that was persistent was how well the online office hours worked. So I have copied a good idea. So thank you, I really appreciate it. As you know, he puts his whole heart and soul into that. He went on a cruise with his wife and he got stuck in Seattle, so what did he do? He rented a car and drove to 2,200 miles back. As Dr. Jones would. As Dr. Jones would. Anyway, one of the comments on 684 was, we need more time with project coaches. I don't want to do these peer reviews. With all due respect, I don't want to hear what the peers say. I want to hear what the project coach says. So we have scrapped peer reviews. So this semester, you're going to get 2 goes around with the project coach. Okay? Alejandro, we're listening, mate. Yes? Thank you. So, I'm worried about a bunch of people.
I thought this was an honor.
I'm not worried about you, I'm just reinforcing the comments. Some people got incomplete because their project is really nowhere. The project coaches couldn't sign off that you were in good standing. So if you got an incomplete, you need to get working with your project coach double quick. Remember, we have until just after spring break in the last semester to defend. Now, it hasn't happened since the beginning of the 1960s that someone hasn't successfully defended their project. Because if you fail that particular thing, you can't graduate. You could have a 4.0 from all of the other classes. If you fail the defense, there's a problem here. It's never happened. It's never got close with me. I've had some MS Stat kids that I wouldn't allow them to defend. They got very cranky with me. But we were not going in front of the audience next week because this wasn't ready for prime time. And they had a couple of weeks of hell to get it ready for prime time. And now they want to be my best buddy on LinkedIn. Imagine that. My best buddy. They keep trying to link with me. Imagine. But I go through that. Look at my hair. It's white for a reason. So, that's my message this semester. Learn from Patty. We need to kick the can down the road at all times. We don't need to make this the most complicated model in the world, right? We're building an electric car, we just need to get it to work. It doesn't have to have the fanciest air conditioning, right? We good? So, we're going to have some more guest speakers who are previous students. We're going to have Mr. Brokelbank from SAS, who's got a new time series book coming out that I'm very excited about. He runs their SAS on-demand business. He's a fabulous speaker and is in great demand, so I'm really delighted that he has said yes. So are we good? The focus this semester is all the hard yards and capstone projects, yes? Good. All right, any questions about 685 and capstone projects? No? Okay. And you can always reach out to your project coach, right? If something's happened, like you can imagine Patty, when she thought she was going to get canned, we had a conversation that day. All right.
So Dr. Shearer,
Yes.
next week's item, what is that work session?
That means that we are going to have 30 minutes here and I'm going to prowl around and eyeball people, both here and online, saying, yeah, tell me what you're doing in your project, sir. Yes?
Okay.
Yes. So you can see there is a great deal of focus on projects, right? All right.
Dr. Shearer,
Yes.
was the
Sam.
Q&A session recorded for those of us who...
It was.
Okay.
So Sam, we labour on Labor Day at Texas A&M, and as a proud member of the working class, it bothers me enormously. Right? It bothers me enormously. My mother was alive, she'd be calling the president of the university. So, so I hope you watched the video. Ali and I did that last week and you saw I got a bit excited a few times. I love time series. The great thing about this is we see how well we do because we always have a holdout sample. Right? See, and you'll see that I have updated the class notes to include all the most recent data. And it's funny how sometimes I was on the wrong screen. Thank you. Sometimes we do well, and there are other times where we do not so well. But we learn from failure as well as success. Thank the Lord you guys are here. Okay. So, we're working up to doing seasonally adjusted, auto-regressive, integrated moving average models. We're just doing the AR part first. Auto-regressive. I had a boss once who said, if you give me an auto-regressive model with the first two orders, I can model essentially the whole world. He was a bit mad, but we'll see. He's not completely wrong. And we're going to model YT as the linear function of previous values. Model YT as a function of previous values. So we have to do a little bit of writing down equations and monkeying with equations to understand how this works. It's beneficial and it's sort of fun. So the first thing you know is that we're going to mean difference the y's. YT minus mu and YT1 minus mu. We're going to subtract out the mu. So we're talking about something that has mean zero. Are we good? So this says the mean difference at time t. So the sales above, the difference in sales above the mean is equal to the difference in sales above the mean last period times phi1. Times V1. So, one of the executive MBA students in Sydney ran a small designer clothes store. And her model was, this month's sales are 90% of last month's sales. She effectively, out of her head, pulled this auto-regressive model. And then the ATs are assumed to be uncorrelated with mean zero. Remember we called these ATs white noise. Now, for this to be stationary, so rule number one, rule number 100 in time series is we develop models ideally for stationary series. We'll see why as we go along. Remember the first two things we need, the mean to be constant and the variance to be constant. So by definition the mean is constant because it's mu. Then if we take the variance of both sides of equation 1, take equation 1 and you take the variance of both sides, you get the constant squared. Variance is average squared distance, so the phi1 gets squared. Subtracting a number from y doesn't change its variability. So you get the variance of yt equals phi1 squared, the variance of yt minus 1 plus sigma squared. Because remember, the a's are uncorrelated. So here's the big deal. You want this variance to be the same over time. So you have to have this phi1 squared to be less than 1. Right? If the variance of yt was twice the variance of yt minus 1, right, we're going to get something that expands. If the variance of yt equals the variance of yt minus 1, that's a random walk, which we decided looked at last week, and that's not stationary. So for these two things, to add up to the variance of t, we need this thing to be less than 1. So we need the actual phi to be between minus 1 and plus 1. In business, we typically have positives. But if we were looking in chemical processes, you can have negatives. But we typically have phis that are positive. So, order regressive models, we need the phi squared to be less than 1. Imagine if the phi is bigger than 1. So this week is twice last week. Next week is twice this week. The week after is twice that. It explodes to positive infinity in a finite time. Do this for fun and put 1.1 for phi. It goes off the page in a few time periods. So this has to be less than 1. Phi1 equal to 1 is the random walk that we saw last week. Now, the autocorrelation function. We're trying to figure out what's the correlation between yt and yt minus 1. Well, it turns out the first one is real easy. If we have this linear equation, the correlation is just equal to phi1. Again, I can go through the math, but this is not a math program. Now, if you want to look at yt as a function of yt minus 2, you have to do a little bit of monkeying around. So take equation 1 and replace yt by yt minus 1, yt minus 1 by yt minus 2, and you get this equation 2. Then you take the right-hand side of this equation and you plug it in for yt minus 1. So yt minus mu is now phi1 times this stuff involving yt minus 2. We got rid of the yt minus 1. And notice that the phi1 becomes squared. So the correlation between yt and yt minus 2 is phi1 squared. Again, the math blows some people's mind. I find if I get a pencil and paper, I can write this down and it works out. But we can see the pattern. This is t minus 1, so that's phi to the power 1. This is t minus 2, so that's phi squared. This is t minus 3, so that's phi cubed. So you get this really neat pattern that says the correlation, right? The correlation is 0.9, 0.9 squared, 0.9 cubed, 0.9 to the 4. What happens as we do that? It goes away, it decays. Again, one of the things for a stationary series is the correlation decays quickly. Is that good? Whereas if that phi was bigger than 1, 1.1 squared, 1.1 cubed, 1.1 boom, it's going to blow up. Yes? So let's look at weekly gasoline prices. I picked 2009 because that was the last recession, and we're doing right up to 2017. So every year I add a new year. And this is what is called the conventional areas unleaded. Right? Conventional areas unleaded. And we have a look at the plot, which we looked at. And here we're going to do it for change in price. I'm going to go back in this class for the whole price, but right now I'm just going to do weekly change in price. The reason I can do weekly change in price is because this series is stationary. The mean is constant over time. The variability doesn't change much over time. You see periods above the mean look at these periods above the mean, and then you see periods below the mean. That makes me smile and says, this is a series with positive autocorrelation. If I tell you that there was a large change in price last week, there's likely to be a large change in price this week. Does that make sense? It will get better and better at looking at these pictures. If you look at all the time series people, they will sit and gaze at this picture for a few minutes. But we're relative novices, but we'll get back. So here's the autocorrelation function. The correlation between the change in price at week T and week T minus 1 is 0.5248. That's not bad. You'd like to have a bit bigger, but it's not bad. Then here's the picture. Here's the picture. The correlation in that plot is 0.5248. The correlation between YT and YT minus 2 is 0.2737. You can see how the points get more spread out. And then I thought, let's go for fun. If this is AR1, right, this is Phi1, our estimate of Phi1. So I'm going to put 5248 squared, cubed, power 4, power 5, power 6, power 7. You see why I did that? I just took the rule for AR1 and calculated all that stuff, right? Now how do we do? The second autocorrelation lag is 0.274. We got 0.275. Hello, I like that. Real data set. The third lag correlation is 0.153. We got 0.145. That's pretty good too, isn't it?
Yep.
The fourth, 0.136, we got 0.076. Not so happy there. 0.0765, we got 0.040. Still not quite happy. So this is not the best way to do this, is it? Is to see how close, it's hard to judge how close these small numbers are. I'm going to give you a much better way that we're going to use every time. But as a first order approximation, AR1 looks okay, right? AR1 looks okay.
Question?
Yes?
So, let's assume that we're doing this weekly, and the event has correlation, but in year. So, week 52, for example. So you see...
Yeah, I have ignored the yearly event. Yes, but I'm going to get there. I need to worry about what happened this time last year. Yes?
But how would you, I mean, when you see the autocorrelation going low, 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 and then high in the 52 or something?
I could, yeah. Oh, yeah.
But how do you explain that with the data that you show that's supposed to be data?
Again, mate, we're learning to crawl along the ground. We can't even stand up yet. Okay? So we're just learning to crawl. When we can stand up and walk a little bit, we're going to get to that. But yes, you'll see in the subsequent slides I worry about week 52. Okay? Now, there's this great thing called the partial autocorrelation function that says, if I've taken account of lag 1, right? If I've taken account of lag 1, is there any information left in lag 2? Right? Or if I've taken account of the first 5 lags, is there any information left in the 6th? This will tell us where to stop. Okay? Now, our model is this, and I'm going to rewrite that as phi naught is mu plus phi 1 mu. So this looks like a regression equation, doesn't it? Where y is yt and x is yt minus 1, right? Remember the people who were starting in the first semester, they got the first homework. It's a usual thing. People are trying to make it way too complicated. They just had to fit a straight line, right? So this is saying that the change in price this week is a linear function of the change in price last week. Yes? So once we've allowed for last week, you don't have to put yt minus 2. You don't have to put yt minus 2. You don't have to put yt minus 3, yt minus 4, etc., etc. You don't need that. For autoregressive 1, it's saying once you put in yt minus 1, the bit that's left over is a random error. Right? is a random error. Do we get that? So in this case, a simple regression with one predictor is the model. Yes? So if we were doing statistical survivor, we could go, in this case, and do a regression of yt of yt minus 1 and check the residuals look like white noise. Yes? So, this is called the partial autocorrelation function. What's left over when you've regressed yt minus 1 on yt? And if you have a look, for this particular case, the partial autocorrelation function is equal to minus 0.0024. And we're going to be able to show you how to decide whether that's big or not. But it's pretty clear here that 0.002 is small. Yes? So this says, having allowed for lag 1, nothing else is important. Yes? So we should consider fitting an autoregressive model of lag 1. So, for an autoregressive model of lag 1, the ACF decays exponentially. That's what I call exponential decay. Or it's damped sinusoidal. We're going to get to that. It's a more complicated case. We'll get to that later in this class. And the PACF has a spike at lag 1 and then nothing that's significant, so nothing outside the blue lines. So this is a beautiful thing. We're going to look at these ACFs and PACFs. They're going to be on the midterm exam. It's a beautiful thing. I love it. I'm very good at finding real data sets. Right? Here, it'll turn out that this is very obvious, because what happens? Look how this thing keeps going, right? And look here, there's just one lag. Yes? One lag pops out of your porridge on the PACF, the ACF decays. You can't control yourself. You say this must be AR1. Right? When we get to moving average, the pattern is completely different. Are we good? Can we recognise that pattern? Yes? ACF goes on. Phi squared, phi cubed, phi to the power 4. It goes on and gets smaller and smaller, but the ACF, just one lag pops out. So, here's where I generated 5 series with lag, with different phis, because I want to give us a feel for what these look like. And we start with 0.9, which is pretty strong, and then we get down to something that's really hard to model, 0.1. 0.1. The correlation between this week and last week is 0.1. Shoot me now. Just shoot me now. It's not going to be a great model. So, I love to use SAS Enterprise Guide. You get the numbers, you can send them to jump. This is phi equals 0.9. Notice this autocorrelation is 0.8974, right? That's our estimate of phi 1. That's our estimate of phi 1. Phi 1 hat. 0.8974. We did a pretty good job, didn't we? And notice this decays exponentially and there is one significant lag. Yes? Notice the up and downs, that there's more bunching together because the phi is 0.9. The correlation between this week and last week is 0.9. That's pretty close, right? Pretty high. So if I tell you that Y was large positive last week, it's going to be large positive this week. Large negative last week, it'll tend to be large negative this week. Yes? Here's 0.7. Again, this is 0.7, beautiful, 0.7027. Notice that the correlation here is not as evident in the plot. Right? It's not as evident. Just flick back and forth. Look at the big up and downs. Lots of ups, then lots of downs. Here, well, it's not as strong, is it? But have a look. This is what gets me excited. One lag pops out of the PACF. I can't control myself, I want to fit an AR of lag 1. Here's 0.5. This picture is even less, this is like the gasoline changing price. Right? It's a fee around 0.5. You can see the positives follow positives and negative follows negative, but the correlation is not as strong. Again, one lag pops out of the porridge in the PACF and these decay. 0.3. Yeah, you have to be old like me and have looked at a lot of time series. It's not a lot of correlation in that series, right? But again, look what happens. The PACF has one lag pop out and this decays. Look at 0.1. Wow. It's hard to see the correlation in that plot. It really is. And 0.1, because we have 1,000 points, turns out to be barely statistically significant. It barely pops outside the blue lines. So we'll see series where the autocorrelation is statistically significant, but small, and we'll smile and say, good luck with that. We need to find something else as a predictor.
So what is the p-value telling you there?
There's no, yes, it's the Box-Lyon statistic that I haven't told you about. I'm peeling the onion. Just control yourself. Hold on to your pants, as we say in Australia. Hold on tight. Dr. Jones told me he could have taught another class if there'd been less questions. I'm going to be ferocious. We drove back from Dallas, and he was telling me all the material he wanted to tell you guys. While drinking 2 energy drinks. So, you understand my dilemma. Alright. So, Alejandro, in your honours cert, I'm going to change the autocorrelation lags from 25 to 55 because I want to worry about this week last year. Whenever I have weekly data, I want to look at, right, what happened a year ago. Just to see if it's seasonal. I'm not sure gas prices are seasonal. Sales are, but I'm not sure gas prices are. So, here we go. What do we see? Well, we see this decay here, yes? We see something barely pop out of our porridge there, outside the blue line, right? And have a look here at week 52. Yes? It's popped out. Now the trouble with that is, we haven't, when we look at just week 52, we haven't parceled out all the information before that, right? The autocorrelation function says, what's the correlation between now and 52 weeks ago? That's high. But have a look at the partial at week 52. Look at that. It's very small. Yes? So what does our newly found knowledge of time series, AR1, tell us? If you look at the partial autocorrelation function, there's one lag that pops out, right? And we've gone back 55 weeks. So I'm always going to start simple and add things if this doesn't work. Okay? So I'm going to model the weekly change of gasoline prices as an AR1 process. Are we good with that? Yes?
Yep.
So, here's the autocorrelation function. As if some of you found out, if you go to jump and you calculate the correlation between YT and YT minus 1 using the multivariate procedure, maximum likelihood thing, you don't get the same answer at the time series. There's a slightly different definition. And then, these blue lines are twice plus or minus 2 standard errors. Plus or minus 2 standard errors. So at each point, at each lag, right, if there's really nothing going on, those little bars should be within plus or minus 2 standard errors. It's like a 5% test if they're outside. Yes? Yes, assuming the world is normally distributed. Roughly. And then, the way I learned this, which was a long time ago, is that those blue bars are like plus or minus 2 over n. You see the 2 here, it gets a bit more complicated than that. But if you had to just come up with a function out of your head, 2 over root n is a good approximation to the standard error. So, or in fact, here it is.
Being what, sorry?
So hold on, I misspoke. It's 1 over root n, the standard error, and then for 2 standard errors, you're going to multiply that by 2. Harry, question?
And being what?
I don't understand the question, sir.
What's n?
N is the number of data points in the series. Yes? Sorry, I get out of control. And then here's the Lyon box. George Box was a great fellow, a very good applied statistician. He wrote a memoir right in the last few months of his life, and he didn't pull any punches. If you want to read English working class speak that's direct, it's a beautiful book, mate. It's a beautiful book. He had this job in the army where he was supposed to blow up these unexploded munitions. He did all these calculations, and his explosives were too strong, and he blew up half the town outside the army base. And they went round to people's houses, literally picking shrapnel out of the china cabinets and the walls. It's a funny story. But a brilliant time series bloke. He actually, what we're doing is we're teaching you the Box-Jenkins methodology of fit time series. That's what it's called. From the start of the 1960s. Now, this p-value is the p-value that this autocorrelation is significant. That's the p-value using this Box and Lyon. So what we're doing is we're doing 55 tests. And when I look at this, this isn't such an interest to me. There's a later part where I get really excited about the Box-Lyon test. Here, I'm not so fussed about it. Right? Here, I'm not so fussed. What I'm looking for is general patterns. General patterns to figure out what model to fit. When I get to residuals, the Box-Lyon test is going to be very important. Very important. But we'll see. So, let's fit a model in JUMP. So, you go time series change in price. In fact, let's be wild and do that. So, you have analyze, specialized modeling, time series. This is all in the class notes. You know I put everything in. Date goes in time, change in price goes in time series. You change the autocorrelation lags to 55. You push OK. Then we go, what do you do in JUMP if you want something done? You go to the red triangle. Red triangle says we're going to fit an ARIMA, and we're just doing AR1. We haven't learned about differencing. We're going to learn about that next. And next week and the week after, we're going to learn about the MA part. We're just doing baby steps. We're crawling on our hands and knees with our mother chasing us. Sandy, you know what that's like. We've got a new child.
Yeah.
Keeping away from the power outlets, right?
Well, not
Yes.
yet. But
That's what I'm doing, because you guys are dangerous right now with time series, okay? So, estimate. We get this up and down. We get the up and down. Yes, we get the up and down. Now we come down here. This says that this estimates this to be an AR1 with phi estimated to be 0.52. Now, when I do this in practice, I can't control myself. What I want to do is I want to have a look at the residuals. I want to have a look at the residuals. And when you look at the residuals, do you see any patterns in the residuals? You'll get better, but I don't see any. But have a look at this, is a beautiful thing. Look at the Box-Lyon test on the residuals. Look at all those p-values. Do you see any red ones? Do you see any red ones? No! There are no red ones. What does that mean? None of them are significant. Right? The residuals resemble white noise, don't they? Once I fit an AR1 to this model, the bit that's left over, the residuals, looks like white noise. So we go in Australia, well done mate, good on you, well done, give yourself a pat on the back. That's a valid model. Yes? Are we good? We understand the logic? We're going to go through all the steps carefully in the class notes? Yes? So this is where I love the Box-Lyon statistic. Look at it. Down to row 55. So Alejandro, do I need what happened a year ago, mate? No. All I need to know is what happened last week. Yes? It's a beautiful thing.
Dr. Shearer,
Yes?
there was an alpha level that you had to choose when you ran it. It was 95%.
There was an alpha level. I didn't choose.
You didn't change it, but it's there.
Okay, so let's do all this again.
I'm just curious.
Specialized modeling, time series. Where do I choose by alpha level?
Where you click on ARIMA, on the red triangle.
Changing price, 55. Time is date. Then I have to come down here to red triangle and go ARIMA.
Prediction interval.
Oh,
sorry.
the predictions.
Yep.
So, on that picture, I want 95% intervals. Yeah, I'm going to tell you that the intervals are rubbishola. You know what that word means? Rubbishola. It's a special word for time series. Rubbishola. So you can put 99, you can put whatever you want. They're still rubbishola.
But that doesn't change the p-value.
I'm not doing p-values here. Right? All it does is change the picture. So if I do, let's say I do 50%.
Yep.
Let's come down and click on the graph. I don't know why it did that. What I was hoping it was going to do was give you an interval, see here, these two here, that are really narrow. It only covers 50% of the data. I call them rubbishola because we'll see that those intervals are not quite correct.
But the p-value is still testing significance at
P-value,
95%.
please don't use the p-value word.
Okay.
Please don't use the p-value.
The
It's
Lyon
really
box
upsetting.
test.
The box test is using the p-value. So,
Yeah.
and these are p-values, right?
Okay.
So let's go back to the original output that I had. These are t-ratios and p-values. So what we've really done is we could have done this using least squares regression, where we took yt and fit a straight line with yt minus 1. The only thing different here is it used maximum likelihood. We didn't use least squares. We'll see later on in the semester when we get into more complicated models, maximum likelihood doesn't always converge, so we're going to end up using least squares. In fact, the latest SAS time series packages, the default is not maximum likelihood, but least squares. Are we good? And then here's the p-value. It says this 0.528 phi is very highly statistically significant. And then these 95% intervals, that's these red shaded curves here.
Yeah, but in the Lyon box test, you still have an associated p-value. On that one, you're looking.
Yeah, a p-value, but I didn't set an alpha for it.
That's by default 5% for being significant.
For it showing up as red, yes. There's orange, red, green, there's all sorts of things in jump, right?
Yep.
But if it's going to be black, it's not going to be less than 0.05.
Okay.
So let's go back to the class.
So, question?
Yes,
So your prediction for, so right now you are feeding the data from the past.
from the past. And we're going to predict all of July and August. So I've got those, hold that. Okay?
I'm gonna hold
Right.
the question.
Then it's again, you know, I was under control when I taught you the regression. I'm going to be completely out of control when we do time series. Completely. Look at those hidden rows, right? So they were not involved in the calculations. Yes? We want to predict those. Good. So let's try and explain what the jump output gives us. First, what we'll see is in a model comparison, we never fit one model. In the project, you're asked to give me your 2 best models. We typically look at a whole bunch of models and pick the best from that. All right? It gives us AIC, which is great if you want to minimize prediction errors. If you're going to live or die by your predictions, it'll put too many parameters, it'll make the model too big. It'll have some statistically insignificant terms. BIC or SBC is the thing you want to use if you want to have the model. So remember from 608, if we had more and more data and we choose SBC to predict the model, to choose the model, eventually we will get the true model with SBC. Right? So if we fit AR models and the true model is an AR model, with a large data set, SBC will pick the right order. So I'm an SBC person. Yes? Then we have R squared. If you think I got cranky about R squared in regression, just wait. Later today I'm going to probably jump off the desk, even though I'm old. I don't like R squared at all. If you look at that terrible model last week about the exchange rates, R squared was 99% and change and the model would get you 5. Yes? We don't care about that, we care about the quality of the predictions. Yes? Mean absolute percentage error, mean absolute error, we're going to talk about those next. And here are your predictions. And then you'll see I cut out of the jump output. Oh, and then here it does weights. It based on AIC. And you know I'm not shy. I've talked to the time series people at Jump. Please don't do this based on AIC. Please order the models from best to worst based on SBC. Because that's what I always do. And that's what anybody does if they want to find the best model, rather than the best predictions. But we'll get to that. We'll get lots of practice. Okay, let's look at the output. Phi1 is estimated to be 0.52803. That's just that number there. The intercept, which happens to be mu in this case, is equal to that. It's really a misnomer to call it the intercept because it's really not the intercept when you fit the regression the way we would think about it. But remember, you have to think about things as the model is y hat t minus mu hat is phi1 hat y hat t minus 1 minus mu. We always subtract the mean. We always work with a series with 0 mean. Sam?
So is that always going to be close to 0 based on the
What's always going to be close?
the mu, the intercept?
No, well again, the mu could be, when we look at Warren Buffett's company, right? Warren Buffett's company, that mu was really big. Every quarter he makes a big new chunk of change. Right? So if we do quarterly sales, that mu can be giant. It just depends. Okay?
You're subtracting before,
There was what, sorry?
you are not subtracting it already, so your prediction shouldn't be 0 because you're already subtracting from the data.
Again, I'm doing change in price. I'm doing change in price. Change in price So it's not surprising because we have a relatively stable system that this change is equal to, hasn't been close to zero. But if you look at change in earnings for some of these companies where they've had exponential earnings, right? Amazon.com, that mean is going to be giant. So one of the things I learned from bitter experience is I park a lot of my preconceived notations about time series. Like I'll think about them, but then I'm going to learn through all this.
But isn't that a contradiction that stationarity implies a zero mean, and then we're using a mean which is not zero?
Yeah,
Yeah.
that's what I was.
No, stationarity implies a constant mean.
Okay, not a zero mean.
Not a zero mean. Could be, you know, do as you want. Yes? Yeah? So imagine you make 10% each quarter. The difference is not going to be zero.
Yep.
It's going to be 10%. Boom, 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 boom. Yes?
He's thinking of the mean for the residuals.
The residuals. What's left over after you fit the model, that's what we're going to live and die by. So when you hand in your project, the first thing I'm going to go and look at is the residual plots. And if I don't like what I see, I'm going to go really crazy. Right? So I keep calling people cell numbers in the middle of the night.
Oh, sorry, one more question. Is it the mu, the average 0.001385, or does the average times the theta or whatever there you have there, which is 0.5282? You see, because I mean your equation says that you have a mean multiplied by a function outside, right?
Yeah, so again, let's be very precise. You notice I've written all the steps down. This is the model in the blue box, yes?
Correct.
Mu is 0.0138473. It's in two places as mu, right? It's in two places. It's called the constant or the intercept estimate, and it's called the mean. So I put that in there, and I put that in here.
I might not be following why the intercept is the mu, and it's not the
That's
mu.
because Jump calls it the mu. I don't like it, but that's what they call it. Okay? Yes? And then they call the constant estimate, right? The constant estimate is what we in 608 and most other people call the intercept, but they call it the constant estimate. So, here are all the definitions. AIC, R squared adjusted, make, MAE. And then I want to do make versus may. Mean absolute error is scale dependent. So that's how close you are, right? We predict the change in price to be 5 cents and it's 8 cents. We're off by 3 cents, right? If we're overs and unders, we still count that as off by 3 cents. Now, if instead of doing it in dollars and cents, we did it in euros, we change the answer, wouldn't we? It depends on the scale on which you do this. Yes? But sometimes we get a good feeling for being off by that. The other one we can do is percentage. And percentage says, let's take the difference between y and the predicted value of y and divide by the actual value of y. This is what we usually do. Are we off on average by 10%, 20%, 5%? We're going to look at an example later. We mightn't get to it today, but it's in the class notes where we can get within 1 to 2%. We can predict the number, the income for Netflix within a couple of percent. It's extraordinary how good the model is. Now, this is terrible if the actual Y's can get close to 0. So if there are a lot of differences, right, if the price stayed the same week after week after week, you didn't adjust the price. So remember, we're doing a series of change in price, and we divided everything by 0, that would trash that measure. So it's like anything, horses for courses. All right, then we have a look at the beautiful residuals. the beautiful residuals. None of the p-values are significant. In 50 of these p-values, well, let's do 100. If we had 100 lags, how many of those p-values would we think should be significant on average if there's really nothing there? We use Diego's 5%, right? We use Diego's 5%. How many of the 100 p-values should be less than 0.05?
5.
5. So sometimes we're going to have a model that has a few colourful p-values, because we're doing lots of tests, aren't we?
Yep.
So the first thing you have to ask yourself is, I don't want to consider too many lags, because the more lags I consider, the more opportunity I have for making a mistake. Yes? I'm testing and testing and testing. Yes? So when I see something like this is the second week of a time series class. Look how beautiful those p-values are. They want to make me weep with joy, right? It's saying that a simple AR1 model models the change in price, produces a valid model for the change in price. Yes? And, yeah, it does. So, assessing model validity. I'm the model validity guy, right? If you really want to jerk my chain and do badly in the midterm, man, this is a good place. There's going to be lots of opportunities for you to assess model validity.
R squared.
Yeah, that's great too. There's a few people in the class of 2019 that still love R squared. Oh, I've got just a beautiful. I've updated some of my examples. I've got some surprises for them. Okay, examine the autocorrelations of the residuals and see whether they're consistent with white noise. Ideally, none of the box-long statistics should be significant. Examine the plot of residuals against time and look for. So it's possible to have all the box-long statistics to be not significant and have a slice of pizza that tells you the variance is not constant. And then we've got another problem, right? Yes, we do. So, let's have a look at the ones that we generated. Here's phi equals 0.9, and again, we get 0.8996. That's a beautiful thing, isn't it? A beautiful thing. We knew what the answer was, and our estimate became, this is our estimate of 0.9. Although we did pretty well. And have a look at the residuals. The original series has very strong correlation. That's in an earlier picture. The residuals have nothing significant. Now, again, we're going to have to do from next week on, we're going to have to start using SAS. So jump is really good to get started. It's good at pictures. It doesn't allow for outliers and level shifts in time series. Right? If I call up the help desk, they're going to hang up on me if I mention that again. Right? So a great way to teach yourself time series coding in SAS is to just go to jump and push the red triangle, create SAS job. And then it's going to give you the SAS code. And here is the SAS code. Oops. Procarima. You tell it the data. You have to identify the model. Var, the variable is change in price. Now, this white noise equals ignore missing is gibberish. And that's there to make the box-long statistics look the same in jump as they do in SAS. You know, the SAS and jump people never agree about anything, and they have a different version of the box-long statistic. So I typically cross that out because I like to look at the jumps version of the box-Lyon and the SAS version of the box-Lyon. Okay? And here we do estimate P equals 1. The P tells you that it's AR. If it's MA, it's going to require a Q. But the P tells you it's AR. It's really weird. We don't have any AR written there, but it's telling SAS, fit me an AR model of order 1. Yes? And method equals ML. Method equals ML, maximum likelihood. We'll come up with some examples later in the semester, and some of the previous students have had projects where maximum likelihood doesn't converge. But we'll get to it. And then you have to add the comments in green. You can put them in such that they always come on, like in your personal profile. ODS graphics on. I like to put plots equals all, because I love diagnostic plots, right? And I'm going to forecast. Well, and here I'm going to say I don't want just the default number of lags. I want to look back 55 so I can look back a year, and I want to forecast. I want a picture of the forecast. So, this is, here's the series YT. Here's the series YT. Here's the autocorrelation function. Here's the partial autocorrelation function. And here's something called the inverse autocorrelation function, which I never look at. You can, so you know I am a man of strong views and strong beliefs. I don't find it that useful. And it would take me 45 minutes to explain it to you, and I don't believe in it, so I'm not going to bother. Okay? You can look in the manual and I'll answer any questions you have. It's never helped me once. Right? It's like your old girlfriend in college. Get over it. Get over it. Stop talking about it. Now, let's have a look at what SAS did versus what JUMP did. Look at the coefficients. 52804, 52833. Close. 001387, 001387. Close. Standard errors. 0043, 0045. So they're relatively close. We'll see from experience the coefficients are generally very close. The standard errors can be a little bit different. JUMP claims it uses modern methods to maximise likelihoods, and some SAS algorithms go back 30 years. Question?
Dr. Taylor,
Yes, go ahead.
let me ask a question that might be sacrilege.
Please.
So, in other technologies such as R or Python, will their answers be different as well?
That's a good question. I've not had any experience of Python for time series. In a previous life, I used to do time series in R a lot. It depends on who wrote, which package in R you're going to use to fit the time series. They have some new ones. There's a fellow called Hyndman, who I taught when he was a young man. He's a bit of a genius from Monash University. So it depends on whose stuff you use, right? That's the answer. It's one of the reasons I don't really like R.
Okay, thanks.
But there are lots of good R packages around. So, then when we have a look at the, yes, Diego.
In the previous class, first semester, SBC and BIC were not the same between SAS and JUMP, but it appears that they are the same here.
They are here. They differed by constants. They're the same thing, they just didn't get the definitions like it. But here they're the same thing. They've got the same formula, a whole 9 yards. Whereas in stat628, they use different pieces of it.
So here, when we look at the summary and the speed statistics, they should always correspond?
They should. They should. And when they don't, we've got a problem using them.
Okay.
So, have a look at the, here's what I really like about JUMP. Look at this white noise test, right? Look at the white noise test. This is the test at the 5% level, this is the test at the 1% level, and look how close they are. They're miles away from any of those, right? So you go, give yourself a virtual pat on the back and say, well done, good on you, mate. We say in Australia, good on you, mate. That AR1 model's a good fit, isn't it? Because the residuals pass the white noise test. Yes?
Could you explain again that the 5% and the 1%?
Yeah, see how it says on this axis 0.05 and
Okay.
0.01?
Right.
So if I had, Antonio, a whole bunch of blocks up here, a bunch of tall ones, yeah,
Right.
that's saying, oh, we got a problem, Houston, right? Yes?
Yes.
So it's the same information packaged in a different way. I find this visually really easy to look at. You know, I get really excited when I fit a model, and all I want to do is look at that plot. If I see something like this, I go, I have a valid model. And if I see a forest of those blue things up above 0.01, I have a problem, don't I?
We got it. Okay.
Is there any, can you see some of them have a significance, or you should see anything?
Ideally, mate, you shouldn't see everything. You know, you should get, my football team should win every week. It doesn't happen, right? We still love it. It's experience, right? Whenever you see a bunch of them go above, you always say to yourself, how can I improve the model? Is there some feature I haven't put in here, right? And remember, we're not trying to come up with one model, we're trying to compare a whole bunch of models, right? We look at the residuals, and again I look at this, what do you see there? I look at that and I smile. There's still a few problems with the model. It's valid. The variance looks pretty constant. I see some outliers. Look at the QQ plot. I see a bunch of outliers. There are a bunch of those big changes in price of nearly 20 cents, right? But the price of gasoline changed from one week to the next by almost 20 cents, right?
So, in the previous regression class, the QQ plot at the tail ends would always dovetail out. So you wouldn't be concerned about that kind of a hiccup at the ends. Is it not the same?
So here I'm going to worry about additive outliers. I'm going to talk about them next week. And yep, they're not that bad. But there's a thing called level shifts, which really monkeys with what happens. If you miss a level shift in your model's going to be wrong. Everywhere. Okay?
So these are absolute residuals. Do you ever look at studentized residuals here, or?
People don't in time series. I've never seen it printed out.
Okay.
Okay? We'll see that there's a great way to do an outlier test in stats, but next question. Okay, and then here are the predictions. Here are the predictions. Have a look what it actually forecasts. And that's what we're going to worry about next. After a while, right? After a while, the forecasts become flat. So think about the model. This says YT this week is a function of last week. Yes? What about the week after? The week after that? The week after that? Remember, the phi gets squared cubed to the power 4. 10 weeks in, we've got 0.52 to the power 10. What's that? Not much, mate. Right? So one of the other things we're going to learn is we have a valid model that fits great. And it'll tell us next week, but not much else. So that's why when we get to Mr. Rubenstein comes and he can predict price 12 weeks in advance. That's pretty golly gosh good, right? 12 weeks in advance. And here are our forecasts. You can actually look at the difference between the forecast. This is the spiky curves and the actuals. And you can notice that there are a bunch of outliers. Right? There are a bunch of outliers where the points are way above, right? They're way above where the model predicted. Yes? Way above.
What's the shaded area?
The shaded area are these prediction intervals that I don't like. So, but I'll tell you why I don't like them at another point, right? Now, in JUMP, you can save columns, you can even save the prediction formula. The thing about saving the prediction formula, it tells you how it calculates the predictions. That yt minus mu hat equals v1 hat, yt minus 1 minus mu hat. That's the one equation we have, right? Yes? And then here is our actual price and our change in price prediction. What it does is it gives you another window. Gives you another window with all those predictions. And we asked for 25, we asked for 25 steps ahead. Remember we looked at 55 autocorrelation lags, and we asked for predictions 25 steps ahead. Which if you think about AR1 is a crazy thing to do. But I didn't want to deal with that then. Now, we're going to use pencil and paper to figure out how to calculate a prediction. Okay? So, the way I think about things, if I can't write down the formula and use Excel or pencil and paper to figure out what it's doing, then I don't really understand it. Does that make sense? And as you'll see, this is how to run on the midterm test. Sometimes, not other times. Is that helpful? So, have a look at, we knew what for week 443, we knew the change in price was 0.023. It was 2.3 cents, it went down. Now, what we want to do is figure out what our prediction is for week 444. That's our first mission in life. We want to figure out this one, right? So we want to figure out y hat t, where t equals 4, 4, 4. Okay? Yes? So the formula is y hat t minus mu equals v1 hat yt minus 1 minus mu, right? So we have to write down the intercept of the mu in the two places, there and there. We good?
Yep.
Right? Remember, we always subtract the mean. Yt minus mu, yt1 minus 1 minus mu, and then the phi1 is what we multiply the yt minus 1 by. Alright? And then all we have to do is substitute what yt minus 1 is. And yt minus 1 is the change in price the week before. The change in price the week before is minus 0.023. It's pretty simple, isn't it? Well, it is. Wait till we get to moving averages. If you don't like this, we've got a problem, Houston. So all we're doing is saying to predict next week, we take last week, right? We're going to multiply it by the phi. We're going to subtract the mu on this part and add the mu on the other part. Are we good?
Yep.
That number works out to be minus 0.011. I didn't do lots of decimal places, minus 0.011. Oh, well, there I did actually, minus 0.0114912. And I got exactly that. Now, what happens if we want to predict t equals 445? Right, we write down the same equation, don't we? Yeah. Now, what do we use for y444? What do we use for y444?
443.
We don't know what it is, do we? All we know is the prediction. All we know is the prediction. So we put the prediction. We put the prediction. So you can see how this is going to get more and more error prone, right? We can predict next week using this week's. Once we predict next week, we've got to use next week's to predict the week after. And then we've got to use the week after to predict 3 weeks out. And 10 weeks out, we've got to use a prediction for 9 weeks out. Yes? So this is not very good after 1 or 2 weeks, right? Yes? It is. It's not very good. And what happens is this thing will approach the mean. This thing will approach the mean. Have a look at what we get, 01384, blah, 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 we effectively get the same prediction. Because 20 weeks out, right, we've moderated that change, right, 20 times. We've effectively used 0.52 to the power 20, which is essentially nothing. Okay?
So Dr. Shearer,
Yes?
we're using maximum likelihood, but let's say if I didn't have jump and I want to do this in Excel, I could always subtract the mean and apply least squares. Am
You
I
could
going to
do
get the
least squares.
same result?
Very similar. Very similar. Very similar. Right? So if I was stuck on a deserted island and I had 15 minutes of battery left and Excel, I'd just use least squares. Okay? All right. And then I'm going to show you. I'm sure one of you can figure out a much smarter way to do this, but here's my way of getting the predictions and the actuals into one file. So remember when we asked Jump to give us the predictions, it gave us this untold worksheet. Then we have our original worksheet. Yep. And then what we're going to do is we're going to use join tables. We're going to use join tables. So what I'm going to do is I'm going to take the original data table and I'm going to join it with the predictions table and I'm going to match the time group. Yes? So that then in the one place I have all the predictions, right? And all the actuals. Yes, are we good? Now if you can figure out a better way to do that, I'd love to hear. So, we get this new series, this new worksheet called Untitled 5, and then we can plot the actual change in price and the predicted change in price. That's over the whole series. And you can see, again, these outliers. We do okay. The blue matches the red unless the red spikes up or down, right? We don't catch the big spikes in either direction, do we? No? And this is just using one step ahead predictions. That's using last week to predict this week. That's the best we can do. Yes? And then, this is the last year. Is that the last year? Yeah, 2017. And here's over July and August. This is July and August. How do we do? The blue are the predictions and the red are the actuals. How do we do? Not real good. So we had a valid model, right? We had a valid model. Practice is not very good. Yes? That's okay. We have to learn how to crawl and walk before we can run. Yes? Yes? So, what I'm going to get you to do, well, let me go on a little bit, then I'm going to get you to do an exercise. I'm going to get you to fit a model for change in oil price. Now, if you think gasoline is hard to predict, I'll give you the tougher one, oil prices. All right, I'm going to do phi negative. What happens if the phis are negative? Minus 0.9 to minus 0.1. They're all on the same curve. The phi with minus 0.9 is the red. Why is that? Because you get big spikes up and down. If the correlation between this week and next week is minus 0.9, I say if there's a big positive this week, next week has to be a big negative. Yep. Yes? Have a look at this dude. That's your autocorrelation function. It's like a damp sine curve, isn't it? Yes? Sine, damp, sinusoidal. Is that a reasonable description? Because we've got minus 0.9 squared is positive, minus 0.9 cubed is negative, minus 0.94 is positive, it flips. That's really hard to interpret, I believe, but have a look over here. It's just a beautiful thing. What pops out of that porridge? Partial autocorrelation significant at lag 1. So that tells you, please try an AR1. Yes? Please try an AR1.
So you can use this for tidal prediction.
For what?
Tidal prediction.
I don't understand the word before prediction.
Tides, because you have the moon cycle and the sun cycle and
moon, tides, sunspots, all these signs people get really excited by this. If you look at, they have monthly temperatures at all of these weather stations across the world. Central Park in New York goes back to the 1800s. You can actually look at the change in temperature on a monthly or even a yearly basis and model that. There's point 7. Notice again we get this sinusoidal thing, but it's not as pronounced, right? Because 0.7 squared, it dies out quicker, doesn't it? But again, we see the lag 1 and we think AR1. 0.5, only 2 of them pop out. But we see this here and we think AR1. 0.3, really hard to see, except one of them pops out of the PACF, so we think of AR1. And 0.1, there's really not much going on there. Saying the correlation between this period and the next period is really small. It might be statistically significant, but it's not very practically significant. Okay? So, what we're going to do at this point is get you to do an exercise in your groups.
Question?
Yes, sir. Question?
Slide 49. So where we have the tree going left and right.
Slide 49.
So
Yes.
You,
PACF, yeah, the ACF going left and right. Minus 0.9. Minus 0.9 squared is plus 0.81, positive. Minus 0.9 cubed.
I understand. The
Yeah.
question is, you told us that we should see a fast decay in the whatever in that chart, right?
Yeah, you have a decay. It's relatively, it's fine. It's telling me because I see that PACF with a really high phi that I still think that this is stationary.
Okay.
I'm looking at 3 things. I'm looking at the graph. I don't see the mean changing there, do you? I see the ACF damp sinusoidal, and I see one lag shock pop out in the PACF, and it's minus 0.9. It's very strong. So I'm going to try AR minus 0.9. Look at my residuals. Yes? We're good. Thank you. Now, on to the I'm going to do this as a class exercise, not as a homework, given all the stuff that's going on in Houston and stuff. Let's just do it as a class exercise. I'll give out the answer next week. Okay? Let's reconvene, please. Is everybody back? So let's reconvene. It was kind of a trick question, because I want to introduce this notion of differencing nets. I wanted you to kind of monkey with part of the answer. The question specifically said, fit a time series model to weekly oil price. Now there's 2 problems. This series is not stationary, right? The mean is not constant, is it? And have a look at these AR coefficients, which after 25 lags still have not died out, right? Yes? Now, can we interpret this PACF in this circumstance?
No.
No, please don't. Please don't.
Okay.
Why? Because we can only interpret ACFs and PACFs of stationary series. And I do this because I had a student in the first or second cohort who went the whole semester and argued with me. Imagine that. Guess who won? Guess who won? right? All we can say here is the mean changes over time, series is not stationary, stop. Try and make the series stationary and come back. Because if people would argue, this looks like AR2, look at the second thing poking out. It's not AR2, right? So, what you can do is you can go down here and do a thing called difference, which I'm going to show you in the class notes. We're going to do differencing order 1, and have a look at the picture now. Differencing is the change in price. So it's this week minus last week. That's what's differencing. So if you see a series that goes up and down, you can't control yourself, you want to calculate the difference. Does that look stationary?
Mm-hmm.
Yes?
Yeah.
And does it look, it looks like AR1, doesn't it?
Yep.
Looks like AR1? Yes?
So, out of my curiosity, does it matter if it's this week minus last week or last week minus this week? Does that have any effect?
Well, you're going to do, if you think about it logically, we're going to do it in time order. This week minus last week. We're trying to predict the next week. You can't do it backwards. Yes? Now, just to highlight, it's possible to double difference the data. And what I've said, and I've become chastened, is in my experience, I've never seen an example where second differencing works really well. Then I put a question on the midterm, and somebody second difference the data and got a better model than I did. Oh, I wept for 2 days. I looked at my model, forwards, backwards, sideways, in French, in Italian, and I came to the class and said, congratulations, it's a second difference. That's on last year's test, so we'll get to look at it. So, it's a chastening business, right? So here, we can do change in price. The other way we could do this would be calculate a new column and call this change in price. And then we go column properties, formula, we go row, and we go difference. And we want to difference the weekly change, and go apply. And you can see that from the 9th of January 2009, there was an increase of $2.06. See that? That's this change in price is really just the difference, yes? So what we just did was analyze, specialized modeling, time series, change in price, and date. We get exactly the same time series as we had before, yet now we call it change in price. So let me have one more sentence. One more sentence. It's a beautiful sentence. It's very important. Because we really don't want to estimate the change in price. We want to estimate the actual price, right? So we're just going to take one more step and do it all together. We're going to take the price and then do the differencing, work on the differencing, and then go back to the price. You get it? Question?
How you did it the first time? Because you didn't know. So not this one. The other
Not this one. What I did the first time was, I did time series of this. I said that's not stationary. I asked for the differences on red triangle. And that's what this is.
Okay.
That's the change in price. That's what we're going to go through in the lecture notes next. But my experience of teaching this is you feel much better if you've done the differencing yourself, right? You understand what we're doing. Yes?
So the third condition for the stationarity check is that the autocorrelation structure remains the same.
Yes, constant, yep.
But but you also later on in the lecture from last time you said that if it doesn't die down quickly, then it means that it's non-stationary. Right. But they're not related, right? Like you could have one without the other. You could have the same correlation structure, but it dies down quickly.
Yeah, you can have everything mixed with everything else. Okay.
So which one do we check?
So I'm teaching you a process to do everything. You're going to look, first you want to start with a stationary series. When you get the series stationary, right, like differencing, change in price, look at the ACF and the PACF. That tells you what to start fitting. Okay? the constant variance is going to show up in the residuals. Yes?
Mm-hmm.
So, trust me, let me move on. So, what we've just done is differencing. Taking yt minus 1, that's the change in price, isn't it? Right? That is the first thing you want to try when the mean changes over time. Yes? That's saying that prices change up and down, or the series change up and down, but the changes themselves are stationary. Doesn't mean they have mean zero. Mr. Buffett's company always has a positive difference between last quarter's earnings and this quarter's earnings. That's why he's a guru, right? So, we start with here, the gasoline prices. Notice that the oil prices were harder to predict. The fee was like 0.2, and the fee for gasoline is like 0.5. It's easier to predict. So we say this is non-stationary. We take the differences, go to red triangle, select difference, put non-seasonal differencing order 1. We're going to monkey with seasonal differences for seasonal data later. And then we're going to work with this series. Now, when you talk to time series professors, like the guy who taught this course to the first cohort, he loves the back shift operator. So, that's 1 minus b to the power 1. Now, I'm just introducing it as baby steps, but when we get later in the semester when I'm going to difference the data, this month minus last month, and this month minus the month 12 months ago, and I'm going to put all that together, we're going to have to unscramble all that, and the only way to do that is with this thing called the back shift operator in algebra. So there are going to be a few slides where we do both of those. But it's not important now. This looks stationary. It looks like AR1. We fit the model, and notice the only thing that's different is we put a D equals 1. So what we're actually doing is we're fitting an AR model to the price by saying difference the model, right? Fit an AR1 model to the change in price, but then it puts everything back on the price scale. It's a beautiful thing. Yes? So, and we got an RE11. What's an RE? We're going to do IMAs and REs. What's an RE? Well, the AR is the order regressive. What's the I?
Integrated?
It stands for integrated. I don't know why they just called it an ARD, right? An order regressive difference. But integrated, the integration part is the differencing part. So if you see RE, it means it's an AR model on the differences. Right? And notice the predictions are now on the actual price. Right? Are on the actual price. So here we go. We get well, I'm going to show you what we get. Now look at this. Please shoot me now, don't torture me anymore. R squared is 0.9945655 mil.
We're done?
Sorry? And it's a terrible model. Terrible! How did we get that? Well, I'll show you. So, here's the model for price. It's an RE11, order regressive, order 1, I is difference. And this is an IR1 model on the change in price. Notice the coefficients are the same. So this box and this box are exactly the same. Right? This box and this box are exactly the same. AIC and SBC are the same. R squared went from 0.2755 to 0.99456. Shoot me down, please, please. How did that happen? The model produces the same predictions, right? Why is the R-squared model for the price?
That's on the difference.
Sorry?
That's
Mark?
on the whole price, but that's.
It's on the whole price, and the whole price changes its mean a lot, right? So if I tell you that this thing changed 20 cents, 20 cents on $4 is a small change, right? So this R-squared thing can be easily manipulated, yes? If the prices are big and the changes are small, you can estimate the changes poorly, but you still get a really high R-squared, yes?
Yep.
So have a look. Is this a good model? Are those forecasts, are the red things match the black things very well? No. But when you actually put in the whole series, it's really hard to tell the difference, isn't it? Yeah.
Dr. Sheeler,
Yes.
so how would you explain that to a business person who doesn't understand statistics? Because, for example,
Yeah.
I had a consultant who came in and they said how much better their model was than mine because they had an R-squared of 1.
So if you have an R-squared of wrong, I'm really going to go crazy, right? I'm going to use the terms nuff and muppet and wood duck. So R-squared, is it really 1? That says y and y hat are the same.
Yep, I realize that.
Yeah, so there's a bit of a problem. So again, the thing here is we're going to live or die by the prediction errors. So in the gasoline one, the same thing happens. You're off by $10 on $60. That's still a bad prediction, isn't it?
Right,
Yes.
so Dr. Sheeler, but my question becomes like, how do you, so like when they're selling it that way, that is such a great model that they can predict the past so well.
Sure.
How do you, but they don't need to predict the future, how do you show people that that's not correct?
So what I say is we're going to live or die by the prediction errors, both in the past and in the future. Please, sir or madam, print me out a column of actuals and predictors, right?
Right.
And let's see, remember in the movie example, we were up by $150 million. And R-squared was 0.986 or something, right? So that's what I say. And we're going to go the whole semester. Sometimes we're going to do really well. We're going to do well with Netflix, hopefully before 9:30 tonight. But we do really poorly on, we do okay with gasoline prices. We do really poorly on oil price. Right? The difference between predictors and actuals is what I live and die by. Yes?
Not to instigate further, but we did both methods, the price and the change in price, and then the RE and the AR. And we got the same box, the same estimate boxes, the same values in there.
Yeah.
But then our R-square was 0.05, not 0.27.
It was our price and this is gasoline price.
This is gasoline prices. This is not,
Not the example.
this is you're doing oil prices.
Okay.
Okay? This is the easy one. So yes, you're right. R-squared is really low on that. Even worse. So if we look at the residuals pass the Box-Lyon test. They look like white noise. So we have a valid model. And again, we can save the columns and do the predictions. And if you have a look, if you sort of stand back, it does okay, doesn't it? Because we're talking about changes of 10 cents on $3 and $4. That hides it. But if you actually look up close, at from 2016 on, here are our predictions. We said basically, you know how the AR1 goes, it kind of damps down towards the mean, doesn't it? And yet the petrol price changed a lot in the last 2 months. So we have a valid model. That's the first thing we need to have. It's not a good model, but remember, we're in the first week of fitting models, aren't we? Yes? We're in the first week of fitting models. I'm going to show you lots of great models. AR model of order 2. AR model of order 2 says it's a phi 1 of yt minus 1, a phi 2 of yt minus 2. Now for this thing to be invertible, you have these horrible conditions. Because remember, what you've got to do is make sure that this doesn't blow up. So you've got to worry about how phi 1 and phi 2 go together. The great news is that jump tells you. It says, is the model stable? Is the model stable? Go back to these outputs. I haven't labelled it. But notice how it says stable. That means here the phi coefficients are less than 1. If it was AR2, it means the phi coefficients satisfy these crazy equations. So with jump and SAS, we get that for free. It tells us whether we're doing something that's stable. Now, here is an AR2 with a positive phi 1 and a negative phi 2. Have a look at the ACF. What does the ACF look like?
Damp sinus.
A damp sinusoidal curve, yes? Hard to interpret, yes? What does the PACF look like? Lag 2. Hello, excuse me, I don't want to yell on the microphone. Excuse me. Please fit AR2. Right, Johnny? Yes? It's a beautiful thing, isn't it?
So, in that case, should you be I2 or A1?
AR2. Alejandro, you're winding me up, mate. PACF has 2 significant lags. Yes? Yes? Look at it. That's lag 2. Yes?
The third one is higher in significance, right?
The third one isn't. The third one is minus 0.0164.
The third one I read is 0.7772.
Yeah, that's I'm looking at the partials.
Okay. Me too.
And then the next one is minus 0.6959.
So the
Fit
third
2, AR2. The third one is minus 0.0164. Nothing.
Okay, so the first one is higher than the second one, right?
Yeah, I don't care about the order. They're both outside the blue lines, aren't they?
Okay.
Yeah? So it says, please fit AR2.
No one, it's just the two.
Yeah, because the PACF has 2 lags significant. If the PACF had 5 lags significant, I'd fit AR5, right?
Okay.
Okay? So I fit AR2, and I get 1.32 and minus 0.705, which matches really close, right? And the mean is 10, and I got 10.18. Yes? And they're my residuals. So the only thing that was different between AR1 and AR2 was we recognised 2 partial autocorrelations were significant, right, Johnny? So it says, please fit AR2. Yes? Yes? Good. Let's look at Netflix. So right now we are not dealing with seasonality. We have to learn the AR piece, the MA piece, the outliers and the level shifts piece, and then we're going to worry about seasonality. So here was my job. Find a product that's not seasonal. That means every quarter the sales are about the same. Netflix. DirecTV is very seasonal because a lot of people buy that NFL ticket. Yes? The football. Watch the 4 screens at once. I don't know how you do that, but some people do. Here's Netflix quarterly earnings. What do you think? We have an increasing mean, don't we? Yes?
Yep.
So what are we going to do? We're going to difference. We can't control ourselves. We've got this new tool. We've got a brand new hammer. We're going to go and difference everything we know this week, aren't we? Have a look at the differences. There's a few spikes. And here I'm doing domestic revenue because Netflix, I couldn't get a model to fit with Netflix total revenue because they got Canada, Australia and the rest of the world joined partway through. So I've got more than one process going and it's really hard to fit a model. You've got to do those separately. This is just the US revenue. Okay? So, this looks like this goes down and this says PACF with one lag. So what are we going to try? AR1 on the differences. Yes?
Dr. Shearer,
Yes?
wouldn't you argue that there is a little slope on the mean?
Oh, sir.
I mean, it's a matter of judgment, right?
Yeah, it's a matter of judgment. So again, what we can do is fit our model, look at the residuals. So this is going to say maybe you need to do second differences. Try.
Why,
So, Sam,
why are the blue bands a lot wider in that?
because we only have, how many points do we have? We only have 2003 to 2016. That is 14 years times 4 points. It's only 56 points. We're not doing weekly data over many years, right? Over 8 years. Yes? So, we've only got 50-something points.
So the other question is, variance is increasing over time? also?
Again, let me get there. Let me get there. Just hold on to your pants, mate. You know, we're serving a gourmet dinner. We haven't even opened a bottle of wine yet. Okay? Yes? So, we get the intercept is 270. These are $1 million. So, this says that the difference, the increase in revenue is about 270 million every quarter. That's a good little business, isn't it? And the fee coefficient is like 0.55. How do the residuals look? They look consistent with white noise. Right?
There is a trend.
There's a trend. Diego, mate, you can make your model as complicated as you want. I'm going to be happy with my thing here, alright? Well again, let's live or die by how well we do with the predictions, the future predictions, as we were talking before. So here we go. Look at the predictions.
Yeah.
13 billion, so look at the prediction errors. 1.3%, 0.1%, 3.8%, 2.1%, 0.2%, and 1%. So these were outside the data. We had a prediction error of 1%. Hello, if I was running Netflix and you could say you could predict 2 quarters ahead, so within 1%, you'd say, I think I might hire you, mate. How much is your fee?
How much can we predict, how much can we stand that prediction being consistent in your experience?
Well, here, because it's AR1, you really only ideally want to do 1 quarter ahead, right? 1 quarter ahead, maybe 2. But I like this example. I didn't make up the numbers. This is a real company's quarterly earnings, right? And if you have a look at the red and the blue, we do pretty well, don't we? Yes? And if you look at the percentage error in the predictions, a couple of percent. So we go back to the online discussion. I would go and say, I don't really care what R squared is here, right? My predictions are very close to the actions. Yes?
Yes.
Yes.
Yeah, thank you, Dr. Seeler. I felt very confident in my answer before, but now I feel really confident in the way that I modeled it. So
There you go. Just give him my email address. I'd love to talk to you.
well, I have trouble getting information from those consultants, so I highly doubt they'll email you.
No, it's okay. All right.
So those 2017 quarters were hauled out?
They were holdout.
Okay, okay.
They were the holdout.
So you can't really claim that you had really good predictions like on the 2016 ones, right?
No. Right? Notice that this stopped in 2016 quarter 4. Right? So what I did, Sam, which is Reggie-Dig, as we say in Australia, is I looked at the in sample and the outer sample predictions. And they're about the same, aren't they? Yes? In fact, the outer sample ones were so good, I didn't want to give a false impression. I could have set you up, mate, and just shown you the last 2 quarters where we did magically, right? Whereas when I did this a year ago, we didn't predict 16 that well. Okay?
Yeah.
So sometimes when I update the data every year, I go from chocolates to boiled mollies, as we say in Australia. from the finest chocolates where the model predicted really well to it just doesn't go that way. So especially if you have what's called a level shift. And you get the level shift, like they change a rule about something, and the whole series shifts up or down, the model's not going to predict that in real time. Alejandro.
If you happen to have more data, do you think you could extend your prediction period? Like
Now again, remember this is AR1, right? And AR1 says
this one?
The previous.
it's related to the previous one. That's not bad. Yes?
Okay, what about if you're hired to predict 2 years in a row?
Well, then we'll say we're going to predict some of the covariates. You give me the number of new stores that Chick-fil-A opens and the ones that it closes, and I can do a better prediction of Chick-fil-A revenue. Okay? Again, it's the second week. This is miraculous. Yes?
Pacifier.
Sorry?
A pacifier for Alejandro, please.
Yeah. So what have we learned? What have we learned? Well, we've learned that you guys are way too strict. You see patterns in everything, right? Yes, Diego? You see patterns in everything, right? You're never happy with anything. Come on! Yes? So, when we have the mean that changes over time, what is the thing we want to do? We want to difference. And we want to fit a model to the differences. For a stationary series, if we see the ACF, decay over time and the PACF have one significant lag, we think AR1. Right? Yes? We fit our AR1 and then we look at the residuals and see if there's any autocorrelation in the residuals. There's no evidence of autocorrelation in the residuals, so that they're consistent with white noise. An RE11 model, an AR1 model on the differences is a valid model, and then you say before you start bragging, how well do we do in the predictions? We do well. Yes? We do well. Great. Now, what we're going to do next time is, what happens when there are outliers and level shifts? So remember in the exercises we did that I asked you to do for this week and that I went over in online office hours? There was the number of passengers at the Austin airport and it shifted down and then went back up. How do we cope with that? How do we fit a model that we believe is AR1 with a level shifting or AR1 with outliers? And if you want to get me cranky about jump, how can you be serious about time series if you don't take account of outliers and level shifts? Outliers are in every business time series. You know, events happen, right? Think about the Hurricane Harvey in Houston. What's that going to do to all sorts of things? Yes? So that's what we're going to do next. And then we're going to start talking about MA, where the pattern is exactly the opposite. You get one lag in the ACF and all this other stuff in the PACF. Don't want to get ahead of myself. All right, so next Monday, I'm going to send you a note about this. The online office hours is going to be moved later. I'm going to be at the State University of New York at Binghamton on a review panel. So 8 p.m. Central Time is when I'm going to hold the office hours. Okay? But I'll send you a note. We good?
Hey, Dr. Shaver.
Yes,
this is
JT.
JT. I got a question.
Yes, sir.
On Monday night, you had your solution already printed out. Did you put it on eCampus by chance?
I did, I think, or did I not? Did I post a solution on eCampus?
I don't see it.
Okay, I will when I get home tonight, okay?
Okay, thank you, sir.
All right. So I will see you remotely next Tuesday, live from Binghamton, New York. So Monday I'm doing the online office hours, and then Tuesday I'm going to do the class remotely. Okay?
We fly to Binghamton, we do it in person.
Sorry? Yeah, if you want to come to Binghamton, you can be the audience. All right, see you then.
All right, guys.
Thank you.